Hello, welcome to Fundamentals of Acoustics. Today is the fifth day of the second week of this course. Today and tomorrow we will be discussing all about Bode plots. So, what are Bode plots? Well, there are two types of Bode plots and we will explain them. There is one Bode plot for magnitude and one Bode plot for phase. And these plots, Bode plots, the first thing is that they are graphical representations of the transfer function, but they just do not represent the transfer function, but they represent transfer function when S equals j omega. So, when we equate S to j omega, then the plots we get Bode plots. The second thing about these Bode plots is they depict asymptotic behavior of h of j omega when in two conditions, when omega approaches 0 and then when omega approaches infinity. So, Bode plots represent Hs when S equals j omega in the special condition when omega approaches 0 or when omega approaches infinity, because they represent asymptotic behavior. Then there are two types of Bode plots. So, we know that H, which is a transfer function, it is a complex function. So, its numerator can be a complex function and denominator can be a complex function. So, this complex function will have a magnitude and it will also have a phase. So, there are two types of Bode plots. One is for magnitude and then the other one is for phase. When we do the magnitude plot, we on the x axis we plot log of omega. So, we just do not plot omega, but log of omega, and on the y axis we plot decibels. Now, the definition of these decibels is that dB equals 20 log h of omega and its magnitude. So, because we are plotting the log of the magnitude of the transfer function, this is a Bode plot for magnitude. For phase, on the x axis we plot log omega and on the y axis we plot phase, and this could be in radians. So, this is phase of h of w, but it is not just h of w under two conditions, when omega approaches 0 and when omega approaches infinity, asymptotic behavior. Same thing here for magnitude plot, when omega approaches 0 and when omega approaches infinity, then the asymptotic behavior of the magnitude is plotted on the Bode plot, and that is what we look at. So, this is the overview. Now, we will look at some simple examples which will make this concept much more clear. Bode plot for simple pole. And right now we will just worry about the magnitude plot. We will talk about phase plot later for a simple pole. So, if there is a simple pole, suppose there is a transfer function h of s and it can be represented just by a single pole, then the transfer function is nothing but one simple pole and it can be expressed as s plus p. So, this is a simple pole. So, the first thing we said is that when we are talking about Bode plot, we equate S to be as j omega. So, in this case h of j omega, or j is just a regular number. So, I can just write it as omega is equal to 1 over j omega plus p. So, the transfer function for a system which can be represented just by a simple pole is 1 over s plus p, and when complex frequency equals omega, then h of omega is 1 over j omega plus p. The next thing is that I have to calculate the value of transfer function in decibels. So, dB equals 20 log, and please remember that h of omega is a complex number. So, I cannot take a log of complex number, I have to take its magnitude in base 10. So, it is 1 over p plus j omega, and I have to take its magnitude. Now, what did we say? We said that a Bode plot is a representation of the magnitude of the transfer function. So, in decibel units, this is the magnitude of the transfer function, but we evaluate this magnitude under two conditions: as omega approaches 0 and as omega approaches infinity. Okay. So, this dB, this becomes, when omega approaches 0, then this becomes 20 log 10 of what? 1 over p. When omega approaches 0, and the magnitude approaches 20 log 10 1 over omega when omega becomes very large, then it becomes very large compared to p. So, I do not have to worry about p. Okay. So, now I am going to plot this. So, I said that the x axis, so this is Bode plot for magnitude. For h of s. So, on the x axis I plot log of omega, and on the y axis I am plotting decibels. Now, I am going to plot two lines. One line will correspond to the condition when omega approaches 0. So, that line is called the low frequency asymptote, and the other line I will plot whereas omega approaches infinity, and that is called the high frequency asymptote. So, the low frequency asymptote, its value does not change with omega, it is just constant 20 log of 1 over p, or it is, because 1 over p its log is minus of log of p. So, it is this thing. So, this value is minus 20 log p. I should be a little more mathematically precise. So, I will put p in modulus, because p may or may not be positive number, or it may not even be real. it may be complex. So, I have to take its modulus. So, this is the low frequency asymptote. And the high frequency asymptote is 20 log 1 over omega. So, what happens? As omega increases, the value of this term, it falls, right, it falls. So, the high frequency asymptote looks like this, it is a straight line on a log decibel axis. So, as omega is increasing, its log decreases and I have a negatively sloped line. So, this is my high frequency asymptote. This is the high frequency asymptote. The third thing about this graph is to figure out where do these two asymptotes meet. So, these two asymptotes are going to meet when 20 log of 1 over p equals 20 log of 1 over omega. That is when these two lines are going to meet. So, these two lines are going to meet when 20 log of 1 over p equals 20 log of 1 over omega. Now, at that condition 20 will cancel away and 1 over p will have to be same as 1 over omega, which means when p equals omega, then these two lines will meet. So, the point of intersection of these two lines is when the on the log axis, on the frequency axis, this value is log of p. Actually, once again p may or may not be real. So, I will put log of p. So, this is the asymptotic response. So, the Bode magnitude plot for h of s has a low frequency asymptote, which is a horizontal line, and it cuts the y axis at the location minus 20 log of p, and then the high frequency asymptote is a negatively sloped line and it meets the low frequency asymptote when p becomes equal to omega. The last thing in this is that the slope of this line is 20 decibels per decade, or actually negative 20 decibels per decade. Why is it negative 20 decibels per decade? We will look at it. So, consider the case dB1 when omega is equal to omega 1 is 20 log 10 1 by omega 1. Now, I am going to increase my omega by a factor of 10, which means that the frequency has gone up by a decade. So, dB2 is equal to 20 log of 10 1 over 10 omega 1, because I want to see what is the slope of this line. So, I am multiplying by omega by a factor of 10 and I will calculate dB2. So, this is equal to 20 log of 1 over omega 1 and then minus 20, because log of 1 times 10 omega 1 is log of 1 over omega 1 minus log of 1 over 10. So, that is, which means that slope. So, what I see is that if I increase the factor by a decade, slope is change in log omega by change in dB. So, that is the slope. So, this is minus 20. change in decibels is minus 20, change in log of omega, initially it is log of 1 over omega, now it is minus 1, log of 1 over omega. So it has gone up, so it is minus 20 decibels per decade. Okay. So once again, to recap, the Bode plot for a simple pole has two lines, asymptotic lines, a low frequency asymptote, a high frequency asymptote. The low frequency asymptote cuts the dB axis or the vertical axis at minus 20 log p position, and it intersects the high frequency asymptote when p becomes equal to, when omega becomes equal to p at that point, and the slope of high frequency asymptote is 20 log negative 20 decibels per decade. Now this is the asymptotic response. If I have to plot the actual response, then I will actually plot this curve, then I will actually plot this curve. These are asymptotic responses. I will actually plot this curve and I will keep on increasing omega. I will start omega from 0. So what I will see is that the curve will look something like this. So the actual curve is below or lower the asymptotic response. Okay. Actual response is below the asymptotic response for a simple pole. So this is the overview for a simple pole, and what this shows is that that the Bode plot for a simple pole, at least the magnitude component, has a low frequency and a high frequency asymptote, and the asymptotic response is a little higher than the actual response, So this is the conclusion of our discussion for today, and tomorrow we will develop a similar plot for a simple 0, and then we will start figuring out how to construct Bode magnitude plots for complex functions. So thank you and have a great day.